Yeah, so good afternoon, everyone. I am Maxwell Tam. I'm part of Team 6165 MSET Cuttlefish.
Hi, I'm Florence Hu, and I'm also part of Team 616 Items at Cuttlefish.
And we are going to be talking about AI and homography. But before we get into that, we did want to talk a little bit about FGC vision in general. And so in FGC, you can really have two different pipelines for vision. You can have your AI with the Limelight 3A, or you can have OpenCV with any camera. And the advantage of doing AI with the Limelight 3A, as you can see on the left right here, it can get the bounding box of the samples really well. It can get the general bounding box, and it's really easy to do that. But if you look on the right, you can see that the OpenCV with any camera, you can get the angle of samples really well. But there is a downside to the OpenCV with any camera, and it's that as you can see right here, it detected these two samples as the same sample because OpenCV only detects on color, and this is an issue as you can see here. Those two samples are the same color and they're touching, so it thinks it's the same color blob, and so that's why I detected it as the same. A, on the other hand, doesn't have this issue, as you can see right here, it detected those two samples as two different samples because AI detects on a variety of different things, not just color, like the shape, the size, and the environment around it. But one thing about using AI with the Limelight 3A camera is that the Limelight 3A camera does have a very small field of view. So it really depends on your use case. If you do want a bigger field of view, you might want to use an OpenCV with another camera. There are some cameras with like 120 degrees field of view, and that is better to use. For us, we didn't really care about field of view that much, and we did have an active intake, so we didn't need to get the orientation of the samples either. So we were able to just intake those samples in any orientation with our active intake. But if you have a claw, for example, you might also want to get the orientation of the samples, and that's another reason to use OpenCV. Um, so we can get into our AI model detection now, and what we were trying to do was go into the submersible, intake a sample of the right color, and deposit it into the basket fully autonomously during the autonomous period. And the first thing that we wanted to do was detect samples in the submersible using our AI model. Then we mapped samples onto a 2D plane using our homography, which Florence can talk to you about later. Then we choose which sample to intake using our priority algorithm, which Florence will also talk about later. And then we'll finally intake that sample. But we did choose to use AI, but it didn't come without cost because we did have to spend weeks and weeks individually labeling 6,000 samples. But in the end, we did think it was worth it because we achieved a 91% accuracy. And a little bit more about how we labeled our samples. Um, we used a program called Darwin V7 Labs, and what this allowed us to do was actually select color blobs. So as you can see right here, we had a color picker. We were able to select this isolated color blob, and it made it a lot easier to label these samples. Obviously, it wasn't perfect because it is color detection at the end of the day. So there's two samples right here you can see, but these two samples, um, they it detected it as the same sample. So we just needed to fix that manually are using the little points and we can drag them around. But overall, it was still really easy to use this program. And another thing about this program too is that you can add multiple team members onto it. So you can see on the left, we have some of our training data and some of our training images, and we were able to add all 6 people on the software team onto this program and have them individually label. And once you finish labeling one set of images, you would send it in for review for another person to review that image and make sure that you didn't miss anything, that you didn't miss any samples or that you didn't double up on any samples. But even after we did label our AI model, we still needed to know which AI model to use to train it. And we did consider PyTorch as one of the options. PyTorch is generally easier for debugging and implementation, experimentation, and it has faster training times on average, but it does consume a lot of RAM during training. So we decided not to use it. It was an option for us. And then there was also JAX, which is fast execution, especially for large scale, and it has a really good TensorFlow processing unit and GPU integration. But it does have a steep learning curve. and requires a deep understanding. So it was more for enterprises and very large scale things. We thought it was a little overkill for our purpose. And we finally ended up using TensorFlow. And TensorFlow works on all types of devices. You can train it on a mobile device to thousands of CPUs. It's very scalable. And you can also, it's a very mature platform. It has a lot of comprehensive deployment tools. So you can do that really well. One downside that it does have is that it has complex documentation. It can be a little confusing, but we were able to figure it out. And one important thing to note with TensorFlow is that the Limelight 3 camera, which is the only way you can run an AI model on the control hub right now, is that it takes a TF Lite, which is short for TensorFlow Lite, and that's directly a TensorFlow file format. So we were able to directly train it into that and then put it on the Limelight 3. We didn't have to, um, if we did PyTorch, for example, we would have to train it in the PyTorch format and then go through a converting process, which may or may not mess up the AI model a little bit, and then we would be able to put it on the Limelight 3. But even after we trained our AI model, we needed to know how much to extend into the submersible to intake a sample. And this isn't that simple because our camera was mounted at an angle, not a top-down view. We did want to be able to see more of the submersible. So um, if you think about it, if you put a sample directly under the camera and then you move it out an inch, or if you put a sample very, very far from the camera and you move it out an inch too, um, the amount it moves when it's directly under will be different than when it's a lot further out in the eyes of the camera because the further you are, the less it will move out. So to solve this issue, we wanted to transform our image into a top-down view, which is why we had homography, and Florence can talk to you about that.
Yeah, so homography is the transformation from one 2D plane to another. In our case, it's the transformation of a distorted image into a flat top-down view. And the factors involved in homography include translation, scale, shear, rotation, and perspective, all of which correct for distortion. So given a 3 by 3 matrix, we can actually calculate these factors and integrate them into our code. So how do we find this matrix? Well, a Python script detects the vertices of chessboards automatically and transforms the angled chessboard into a top-down view. And so this is done using OpenCV libraries functions called find chessboard corners and find homography, which basically just eliminates user error and makes calibration instantaneous. Once a top-down view is obtained, a homography matrix is then calculated for use in our code. And again, we use this to determine the locations of the detected blocks. And in our case, we just happen to use inches. And next, I think Maxwell is going to do a quick live demo for us.
Yeah. So I'll run the homography script really quick. I can do Python the homography calibration.py. And as soon as I run that, it brings up two windows. So the first window on the left that you see is the image that we took from our Limelight 3 camera of the chessboard. And then on the right is the picture of what the OpenCV script should be looking for. So it's the actual chessboard right here. So if I click the key C, which is the keybind for automatically detecting all the corners, you can see on this image right here, it detected all of the corners of the chessboard automatically. And then on this image right here, you can see the corresponding colors of all of the corners and what they correspond to. So now if I click the key H, that um, automatically brings up the transformed view. And this is this chessboard from this image, but in a top-down view. So it automatically transformed it. Um, it's in the top-down view, and we can use this top-down view in the code to translate samples into that top-down view and move them around. It's just really simple when you're looking at it from a top-down view. And you can see right here, it used this matrix to transform it into the top-down view. So there's a Python version right here and a Java version right here. And you can use whichever one you want in your code um, to actually transform your samples in real time. So if you're using the Limelight Duo camera to do your processing, you'll probably do it in Python using the Python snap scripts on there. Or if you're doing it in Java on the control hub, then you'll use the Java version. And Florence can continue to talk about priority.
Yeah, so after mapping the block positions, we run a priority algorithm to pick and choose the desired color sample using several factors, and the main ones will be shown on the next slide. So the first is proximity to opposing aligned samples. For example, red samples blocked by blue samples are given lower priority. And in general, if opposing samples are in front of a potential target, then the robot will actually not intake that sample. And another thing that our team considered this past season was that we used an active intake, and so it required a clear front pathway. And this is in contrast to like a top-down claw approach. And so this is kind of why we had proximity. The second is distance from the robot. So closer samples are typically easier to intake and they're given higher priority. And then, of course, the third, there are physical limits. And so the target can't be too short because our intake wouldn't work right up against the metal bar of the submersible for those who are in the Into the Deep season. And it also must fit within the extension limit. So in this example, we don't want to intake the red sample indicated in black with a black dot because there are several blue samples in front of it, by proximity, and we might instead choose, the bottom left red sample indicated with the green dot because the path is unobstructed. And another thing to note is that each of their criteria are weighted by their importance. This means typically proximity to opposing samples are weighted more heavily than something like distance to the intake or to the robot. And that's what's shown here. Instead of turning to the closest blue sample in terms of distance to the intake, the robot instead intakes the one on our left because on the right side there's a red sample in front of it. And so just an overview of the entire process. We first detect by activating our AI pipeline. We map out the samples, so which means we calculate the exact extension distance and turning angle using homography. Um, we choose and calculate the highest prioritized target, and then finally we intake the sample. And that kind of wraps up what we had about this. Are there any questions?
Awesome. Yeah, we can do the same thing. We can take one in-person question and one online question. So if anybody in person has a question, you can raise your hand and I can bring the microphone to you. Yes.
My question is short. You can repeat it.
All right.
For the homography, did they do that in OpenCV on the control hub, or was that part of the line?
So the question was, for the homography, was that done in OpenCV running on the control hub or running on Limelight?
We did end up running it on the control hub for the homography, but the way we tuned our homography, we did it externally using OpenCV on a Python script, using that script that I demoed to transform the homography from the angled perspective to the top-down image, and then we use the homography matrix on the control hub in Java.
Awesome. Do we have any online questions or any other potential in-person questions as well? Okay, so Navia asked in the chat, would you consider Python or Java to be better for homography?
Um, to be honest, I don't think that there's much of a difference between the two. There's OpenCV functions both in Python and Java. Um, It it'll probably depend on other factors. Like for example, if you run your Python on your Limelight 3, then you're not stealing processing power on your control hub, which you might need for other things like running motors and servos. Um, so, but if you do run it on the control hub, then it might be a bit easier. You don't have to communicate back and forth between the Limelight 3 and your control hub because ultimately you are running everything from your control hub. So it's a preference choice, but it should be the same for both of them regarding specifically homography.